Any questions? All right, I will stop this share and I will start another share for you, Don.
Okay, Bruce.
Bruce coming up next?
Yeah,
Okay, sorry.
Introduce, so
Okay,
I'll show you.
and here's the clicker. I tested it, it does work.
So hey everyone, it's good that we're all together, at least many of us here. Don's already had several kind of introductions tonight, but it's really nice to be able to introduce Don Miller, who is both a CCAS member and, as Dave pointed out, a recent NASA ambassador. So this is going to be his debut presentation. So like many of us, Don is not an astronomer by training. He actually has both bachelor's and PhDs in chemical engineering and has had, before retiring, a career in the pharmaceutical industry and in marketing. But he's had a lifelong love of astronomy, and he's managed, I think, pretty creatively to combine it with a love of the outdoors, especially climbing and hiking. So he's probably hiked in more national parks than I could count. He's gone to Sweden to see the Northern Lights, hiked in Patagonia, and even made base camp at Everest. So he's a pretty adventurous guy. But when he became a NASA ambassador and he was talking to me about a talk, he said, you know, what could I present on, or what should I present on? And I said, well, we've never had a really good presentation around Venus, either what we know about the planet, some recent discoveries, unanswered questions, and planned missions in the near term. And I think you will see Don has done an amazing job in putting together a really top-notch presentation for his debut. So without further ado, Don, it's all yours.
Okay. Thanks, Bruce. Evening, everybody. Great to be here. Given this my first talk, I hope it goes well as a NASA ambassador. So when I talked to Bruce about Venus, I thought about, there's a lot of probes that have been to Venus or will be going to Venus, but rather than just go through a litany of probes, I sort of wanted to put it in context. One, what do we know about the planet? And also, what is it that is actually making it interesting for us to study that planet? So let's see. Let me get the. So basically, there's been about 47 flybys or probes to the planet Venus. NASA hasn't been back there in 33 years. Magellan was the last probe that actually went to the planet on purpose. Now, there has been the Parker Solar Probe that went by and got some reverse images of it, but otherwise, they haven't really gone back. And you might say, well, why not? One is going to be obvious from what's going to be in the next few slides is it's a pretty inhospitable planet. It's very challenging for space.
No, I just jumped on and he was just starting.
Hello?
I'll get it. I'll get it. Someone's not muted. I'll get it.
Okay. But also it's a matter of its competition. NASA has spent about a little less than $3.5 billion on probes to Venus. But when you look at Mars, they spent almost 30 billion to go to Mars. So there's a lot of competition within NASA for its funding, besides going out to Saturn, Uranus, etc. You got it?
Yeah. The people came on.
Okay.
It was not a second.
Okay. If you could mute online, that'd be great. Thank you. I'll discuss, as I said, the characteristics of Venus, and then why is it important to study this planet? It's more than just it happens to be our neighbor. I think you'll see that it actually can tell us a lot about planets and the evolution of planets. Questions that we are still asking today, I want to go through that and decide, look at how we look at the probes that I'm going to discuss at the end of my talk in light of the questions we're trying to answer. And then at the end will be the future probes and in context of what we know and don't know. So this is a great picture of a transit of Venus across the face, or the image of the sun. If you haven't seen it, this was in 2012. The next one is in about 95 years. So if you can wait till then, great. I don't think I will make it. And so there's two great images here. And actually, the transit to Venus has been getting science for mankind for centuries. Back in the 1600s, Edmund Halley actually proposed we could use the transit times of Venus across the face of the sun, trying to figure out the distance from the Earth to the sun. He unfortunately didn't live long enough to have that happen because it came the next century in the 1700s. And there were basically expeditions that went around the world to get different angles. So they could use basically trigonometry and Kepler's third law to calculate the distance to the sun. And interestingly enough, Mason and Dixon, from Mason and Dixon fame here in the United States, were one of the teams that were going around. And if you haven't read that story, fascinating story, because they ran into all kind of problems trying to get to where they're going. I remember it was Borneo or someplace they were trying to get to, something exotic. But they finally did get there, made measurements. And they came up with a value for the distance to the sun of 95 million miles, which is pretty close to our value today of 93. So they did a pretty good job. Still getting somebody done. I don't know if there's any way to get them off there. Who's ever online, if you could mute, please.
If you're on Zoom, please mute. The whole auditorium can hear everything you say. Please.
Hey, Don, it'd be great if you would share the screen.
Okay, let me try this again then.
This is to pause to refresh.
Yeah,
Any
let's start
questions
again.
so far?
All right, let's start it up again. So everyone has to be quiet when you're on Zoom, please. Let me try it again. Okay, mute everyone.
They're not muted.
There it
you
is.
go.
That's who it was. Okay, now
Share screen.
share screen. Sorry. Slideshow. All right,
All
sorry, we'll get it figured out.
Let's start again. I'm going to give you a time. No, we won't go through that. All right. So this is, I titled this talk about Venus, but it's really a stealth talk about exoplanets. We've just logged our 5,000th exoplanet. Quite a milestone considering it wasn't that long ago. We didn't know if there were any planets around other suns. So a lot of you are coming in, but how do we know if, say, we do find an Earth-sized planet, exoplanet, if it's like Venus or like the Earth is today? Very different worlds. And how do we tell them? And does that mean that a planet was always like that? So Venus is the perfect opportunity for us to learn about planet evolution and habitability. So keep exoplanets in mind throughout my talk. So let's look at a few facts of Venus. One is it's the closest planet to the Earth at when it's close approach, about 0.28 AU. Its year, a Venusian year, is 225 Earth days. Very close to the Earth in size, about 95% diameter, similar density. So a lot of people have used those facts and said, hey, this is a twin to the Earth, before they actually realized what this planet was like. So is it really a sister planet? Probably not, at least as we stand today. It's 28% closer to the Earth than the sun, so you figure it's going to be hotter. Question is, how much hotter should it be? Let's go to the next slide. Basically, looking at actual tilt, we know the Earth has a tilt of 24.5 degrees from its orbital plane around the sun. Venus has 177.4. It's the only two planets in our solar system actually rotate clockwise. Everyone else rotates clockwise, counterclockwise when you look from above. Is it flipped or did it just reverse direction? Some people think due to the thick atmosphere, it actually slowed the planet down and caused instability, which caused it to flip. Other people were saying, no, it's always been the way it is. It just slowed down and then reversed direction. So unfortunately, no one knows the answer yet. This is one of those unknowns in science. But it's fascinating that it has this. Surface temperature, 475 degrees Celsius or about 900 degrees Fahrenheit, more than you need to melt lead. You think, well, it's closer to the sun. Well, it's more than that. So let's go. I'm going to go down here to this table. I guess I'll stay over here. So I have this nice little table here showing the terrestrial planets, Mercury through Mars. SAV is actually the energy in watts per square meter at the distance those planets are from the sun. You can see Mercury gets a whopping load. Venus gets a fraction of that. We get about, well, not quite, a little more than half of what Venus gets. And Mars gets a small fraction of that. Now, if you look at the albedo, which is alpha here, this is basically the reflectivity of a surface. So if the albedo is 1, it's a perfect reflector. If it's 0, it's absorbing everything. We have Mercury that has a 0.1, so it's a really good absorber. Venus, because of all the clouds, it's 0.75. It's a pretty damn good reflector. Earth is 0.3 and Mars is 0.25. You say, well, Don, what's all this about? Well, you can actually take what's called black body calculations, where basically it's a perfect absorber and emitter of radiation. And then if you know the emissivity and the amount of energy hitting it, you can calculate what should the temperature of that planet be. And if you look at Mercury, the temperature is predicted to be 437 degrees Kelvin. What the actual observed, 440. It works really well. Okay, and you jump out here to Mars, 209 predicted, 215. Again, pretty good. You can see, it's a pretty cold planet. Now, if you look at Venus, the prediction says 232. What? It should be below freezing point of water. But the real temperature is 435 K. Or 735 K. So it's really high. And this is a runaway greenhouse effect. So what you're seeing here is greenhouse effect. And interesting is to look at our own planet. Prediction 255, minus 18 degrees Celsius. We're far enough from the sun that we should have frozen planet. And that was actually a concern for many years about how do we explain that the planet should be frozen. But the presence of water basically distributing the energy around our planet, and the fact that we have a little bit of carbon dioxide, we get a little greenhouse effect. We have an average temperature of 15 degrees Celsius, and hence we're all here. Interesting analysis, right? Composition of the atmosphere of Venus, 96% carbon dioxide, 3% nitrogen. Just for comparison, Earth's composition of CO2 is 0.04%. Venusian day is 224 Earth days. Interesting fact, it's the longest day of any planet in the solar system. And it's just slightly different than its rotation period around the sun. So it's not tidally locked yet. Once had a shallow ocean. That's debated, but most people feel that it did have a shallow ocean at one period of time. How do they know that? They looked at sampling on the gases and looked at the deuterium to hydrogen ratio. Given that deuterium is heavier, if you get a very high ratio, you know that you've lost a lot of the hydrogen, and they don't have, well, you're going to learn, but they don't have protection, so that they're losing the hydrogen. So why is it the way it is today, and was it always this way? So it's really about evolution of a planet. These are some of the current questions. And why did it evolve the way it did? Did it ever have life? I mean, knowing what the planet's like today, you say, well, hell no, it never had life. But we're not sure. It actually might have had life. And you'll see at the end of my talk, maybe you'll agree with me. Why does Venus not even have a magnetic field? If you look at the predictions for the surface temperature, the core temperature of Venus, it would be about the same as the core temperature of the Earth. And we know the masses are about the same. So you would think you would have a dynamo going on. Why don't you? And keep that in mind as we go through the talk. And no visible plate tectonics. Is that separate, or is that connected to the fact that there's no magnetic field? Think about that. All right, let's delve into the science a bit. What we know currently in understanding the geology of this planet, I think, is going to be key. So I'm not a geologist by training, but I was lucky to steal some geologist slides. Okay, so that's what I'm using. So here we have this beautiful false color image on the right-hand side, showing from radar as well as from measuring altitude on the surfaces. The dark color areas are flat, low-level areas, and the lighter colors are higher areas. And if they're white, they're basically broken up areas. And that has actually ramifications for, is the planet volcanically active today or not? So it's a young surface. There's only about 1,000 craters on the surface of this planet. If you look at the moon, which hasn't had any atmosphere ever, there's uncountable number of craters on that. So this is a very young surface, very comparable to our own planet in that regard. Volcanoes everywhere. About 80% of the surface is covered with volcanoes. Huge mountains up to 10 kilometers high, higher than Mount Everest. And not only are they high, they're huge going across. And they have long rift zones, which are basically linear cracks around volcanoes. 55,000 kilometers. We have nothing like this on our planet. You'll hear me saying this over and over again. It's an alien world compared to what we have. This is some pictures up here. You can see on the top left, rift zone going through. This is the tallest, Mount Mons, it's the highest volcano on Venus. Beautiful false color here, showing what appear to be different lava flows coming down and the emissivity of the surface. And here we basically, again, this is looking at what looks like young lava flows in the lighter color in the bottom here for you online, and darker, flatter areas would be older ones. And these are actually shield volcanoes on the bottom right. So as I said before, we have huge mountains, very high, but 4,000 to 6,000 kilometers wide. Okay, so these are planets that this is mountain ranges like we don't have on this planet of ours. So let's look at surface geology. How does it compare to the Earth? So what I have here on the right is an image of the Earth, but it's not as we would see from exactly our resolution. This is shown at the resolution that the Magellanic probe had, which wasn't very high. And on the right is Venus. So if we look at the Earth here, you can see right through like the Atlantic here, you can see mid-ocean ridges, very visible. You can see mountain ranges where it's happening on the surface of the continents. You can actually see all kinds of ridges here. And just for reference, crust on the Earth varies. If it's an oceanic crust, it has a higher iron content and it's more dense. Generally density somewhere around 3 grams per cubic centimeter. If it's a continental crust, what we're standing on now, it's lighter, much more like granite, and it's about 2.7 on average. So it floats. We're actually literally floating on these heavier surfaces. We have no idea on Venus what the surfaces are truly made of. This shows basically this resolution. What you basically can tell from this is a few things. One, it's generally flat. Look at that. This is all low-lying area, the deep blue. So it's generally flat with just small amounts of high areas. Are those high areas, question mark, previous continents when this maybe had water? Not, no. Is the composition of this high areas similar to our continental mass, meaning more granite-like, or are they, and vice versa, does this have a lot more iron? We don't know. So this is some of the things that the future probes need to really look at. So as far as we can see, looking at this, you see it's relatively flat. No plate tectonics are visible. No magnetic field is known. And right now, we don't know that these are continents, but that's a question we have to answer. This is actually a close-up of the Alpha Regio region, which I'll come back to later on in the talk. This is one of those areas that we think is potentially a continent. These stand up about 1 to 2 kilometers from that flat plain that's most of the planet. So they really stand up. But is it really a continent? We don't know. Again, the same picture on the right. Stop me if you have any questions. So before we had a lot of data, and truthfully, we haven't had a lot of data in the last few decades. There's only been a few scientists who've really been dedicated to studying Venus and trying to understand, what goes on in this world. So what were considered facts decades ago really might be more likely considered to be myths. So let's look at these. One is Venus is outside the habitable zone. And is that true? It's really resurfaced a long time ago and it's geologically dead today. There's no plate tectonics. Yes.
People are not seeing this.
They aren't seeing it. Okay. Give me a chance to have a drink of water.
Yeah. Let me see if I can get it straightened out. I think the one thing probably.
As a plug, I'm going to be giving talk on the return to the moon at the Chester County Library System in June. And then once the Webb's telescope images come out, I'll be doing a talk on the first images. I don't know what, probably in the library system, but you may also do something with the club.
You haven't read the data that all stuff yet?
I do know what they told me. We just had a briefing session and they said, hey, we don't know the exact date when the picture's going to be there, but we'll tell you in mid-May.
Okay.
Okay. 2, we're not telling you yet what it's off. So I don't know yet, but
Please let us so we can put it out there.
absolutely.
So our members can-
Yeah, at the very least, we can do that. You can either come in on my library one, or you can do something for the club, whatever we want to do. I'm just going time with that. I can do a little soft shoe. My wife was a big apple.
All right. Advance it
Keep
some.
coming back to that slide, though.
Yeah, where were you at? Tell me when to
I
stop.
was just on to the facts and myths.
So Don, we're still seeing the other screen. So we're not seeing the presenter slide. We're seeing just the regular
Let me just share the whole,
deck. Yeah. If you're on a Mac, I know sometimes they have problems with screen share.
what are you sharing, the app, or are you sharing the whole?
Here's. I don't know why it opens up multiple windows.
Yeah, I don't know why that's happening either. Can you tell it just to share your desktop so you'll see everything?
No.
That's weird. I didn't see that on yours.
Put this down.
You close my presentation and reopen it. I don't know why it's open multiple times.
So next time I'm gonna use two computers. I can't monitor Zoom's problem. I tried to my phone and I can't. So there's your presentation. You want to try it just this way?
Yeah.
Let's try it that way then.
But are they seeing it?
Let's just do without, well, let me try it. Let's do without a screen show. Let's try it that way. What you can do is,
You'll see all my secret notes though.
no, not necessarily. So let's see. About where were you?
I can page
We'll
up.
try it this way.
Go back. Yeah.
Because this is how we did Dennis's one time. We had problems with that.
Too far. Yeah, way too far. Trying to skip, you're trying to shorten my talk.
Hey, Chris, can you see this now?
Yeah, I can see what you guys can see on the big screen there.
Okay, we're gonna go with that then.
Yep.
That'll work.
All right, so I think this is where I left off. So let's go with the first one, the habitable zone. One of the key things in the habitable zone is you think about Earth's in the habitable zone and it's only us in the habitable zone. So is that the way it's always been since the beginning of the solar system? The answer is no. So you have to consider the habitable zone's fourth dimension, which is time. So this is a nice cartoon showing on the x-axis the relative radius or orbit, the radius orbit relative to Earth's. So Earth being one, and then the mass of the star. More massive stars being brighter and hotter, lower mass stars being cooler. So the habitable zone, if we're predicting that for these stars, would be this blue area that's shaded in here. And we put the solar system on here basically just to give you context of where that is versus our solar system. So Earth right now clearly is in the habitable zone of our solar system today. But was it always that way? This is really, think of this as a snapshot in time. The sun hasn't been as stable as it is now, and as it ages, it's producing more and more helium. As it produces more helium, the density goes up in the core. As the density goes up in the core, guess what happens? The rate goes up. It gets getting hotter. So it used to be about, when it first formed, about 25% cooler than it is today, approximately. So if you look back 3.5, 4 billion years ago, when it was an early early age of our solar system, now you see that Venus was in the habitable zone, and Earth and Mars were probably just outside of it, but Earth has an atmosphere and an ocean. So given that, it probably always had liquid water. Mars, we think, probably had a very early ocean and may have also had liquid water for a short period of time. Okay, so Venus likely was not in the zone today, but we know it isn't, but was likely the very first planet that was in the habitable zone. So when you're saying the question of could there ever be life on Venus, why not? You know, if it may have happened. So this is an interesting one. If you say, okay, what are the processes we need for life? Well, as far as we know life today, you need liquid water. You need volcanic and tectonic activity. Why? Because this is actually bringing nutrients to the surface. It's keeping a dynamic equilibrium with the planet between the atmosphere, the surface, and the core. So this is actually producing the energy we believe needed for life. So if you look at the planets, Earth, as far as we know, and this is by age, you know, the first 500 million years of our solar system, period of heavy cratering, you know, and the planets were all in a turmoil at that point. But then that actually died off. And then you have essentially a very low but consistent level of cratering since that time. So Earth, if these brown here represent volcanic tectonic activity, probably has been active since the very beginning, all the way up to we know it's active today. Water, far as we know, it had surface water as long as it's been in existence, at least after the heavy cratering period. Venus, the thinking is, it also was volcanically active and very likely is active today. We just haven't proven that yet. But if it wasn't active, if it's not active today, it was active not that long ago, and I'll show you some slides in a moment. Surface water, the thought is, it probably had surface water for a long time and only recently lost it in geologic time. So again, we think back to the habitability. Venus could have had a long period where it actually had the potential to produce life. Mars had early volcanic activity, but we think that ended a long time ago. And as far as the water, it lost it also a long time ago. It's a much smaller world than Venus and Mars. It cooled off too much. Its core temperature is somewhere around 1500 K, where our core temperature is about 5800 K or more. Okay. Mercury and the Moon never had water. So you can see the Venus outside the zone may not be true. And then there was a National Academy of Sciences in 2018 did this work on what is consensus study report on what's needed for life. So these are planetary factors expected to do habitability. Ocean with on the planetary surface. Stable secondary atmosphere. The initial atmosphere of all planets, like our initial atmosphere, had no oxygen. It was very different than what we are today. The early Earth, we would not recognize. So stable secondary atmosphere, including volcanic outgassing. I'll explain why that's key in a moment. Tectonic volcanic activity and weathering processes to replenish it. You need a feedback loops on the planet to maintain stable conditions. And then internal energy budget. What do I mean by that? Basically, you have to have enough energy in the core of the planet that actually can drive convection, formation of the magnetic field to protect the planet from the solar radiation as well as gamma radiation such from outer space. And feedback between all of these processes. So it's a complicated thing that you're looking at. So this is a little cartoon. You probably heard a few years ago, and I'll mention it in a few slides, Venus might have life in the upper atmosphere. So this Cloudland Observatory high up in the atmosphere, could you actually have life up there? No planet's better suited, is my point, than Venus to study these questions to us. So let's go into why is tectonics and having plates important and having geologic volcanic activity important. The reason is on Earth, it connects the interior surface and the volatile processes that are going on. So basically you have an oceanic plate. Remember I said it's denser, more iron, and actually subducting underneath, going back into the convecting mantle. You have a continental lithosphere, or the outer layer of the planet, which is then basically being pulled down, going into the oceanic plate, and then also getting subducted. And meanwhile, you also have ridges and volcanoes that are bringing that material back to the surface. So it's an interchange between the different zones of the planet that are causing these things to occur. So on this one, what I've shown here, volcanism in red, subduction in basically a purple. So basically the volcanism releases volatiles from the interior, subduction recycles those volatiles. So it's an interchange. And let's look at what that means from the point of view of a key factor that differentiates us from Venus. You know the atmosphere of Venus, it's a crushing atmosphere. I didn't mention it before, but it's about 100 atmospheres on the surface. Huge amount of carbon dioxide is on its surface. You say, where did all that carbon come from? Does Earth not have as much carbon? The answer is Earth has as much carbon as Venus has. The estimates are very comparable carbon budget. So why don't we have the same problem? Earth recycles carbon dioxide on a time scale of about 500,000 years. How does it do that? It does that by this exchange. Basically, rain occurs on the land. Basically, you have weathering occur, basically causing the carbon dioxide to form carbonic acid, interacting with the rocks. That goes into the ocean. You also have sea creatures that have the seashells, which are carbonate, forming these carbonate materials, which then settle at the bottom, subducted under the plate, into the center of the planet. Meanwhile, the planet has volcanoes, which are producing CO2 coming back out. It's an intricate interchange. And you say, well, wait, is there a feedback loop? Absolutely. Speeds up when the climate is hot. So when you get more rainfall, more CO2 is coming out. When more CO2 comes out, guess what? The planet cools off. When it cools off, when it becomes cold, CO2 goes back up. So it's a self-regulating system on our planet that's helping maintain us so that we don't have the carbon problem that Venus does. So you probably already can guess what I'm going to show you next, which is Venus looks very different because it doesn't have these. So this is just showing an interesting fact. I won't go to the left side, too complicated. Basically, the beginning of our planet, as I mentioned before, was very different than what we have today. We would not recognize it. We couldn't survive on it. There was no oxygen in the atmosphere. For about the first, from after the solar system settled down, for about the first billion years, there was essentially no oxygen in the atmosphere. But algae did start forming in the early oceans. And we have the event, which is called the Great Oxygenation Event. Amazing. When you look at this, the plot of oxygen going from 0 and it bumps up to almost what we have today. And this happened basically 2 to 3 billion years ago. So that thought is that occurred because of this interchange and the nutrients coming out from the volcanic vents under the sea, producing the right environment for things to happen here. We have lightning, which also produced the amino acids necessary for the formation of life. And another key thing that the tectonics does for us, besides all that beautiful control systems, it actually cools off the core of our planet. And it takes energy to run that tectonics. And when you use up that energy, it's causing basically the core to cool off. When the core cools off, that's causing convection. When you get convection, this is liquid iron down there. It has electric currents going through it. Once you have that flow, you get magnetic fields. Hence, you get our magnetic field for our planet. If you don't have, the thinking is if you don't have plate tectonics, you probably don't have a magnetic field. So what started plate tectonics? And why is it only on Earth? We haven't found another planet yet that we've seen that actually has plate tectonics. How and when did it start? The thought is it began back in the Archean period about 2.5 to 4 billion years ago, when the lithosphere, which is the outer layer of our planet, was a lot hotter and thus more mobile. Subduction is thought to be the first step. Basically, scientists around the world essentially agree that subduction is the first step to starting that. But it's necessary, but is it sufficient? It's not clear that that's the case. Little evidence, little evidence, oh boy, what is going on here, guys? Little evidence exists for how you can actually decide what's going on, and more research needs to be done. Umpteen theories. I was going to start listing theories, and I just started getting swamped with all these theories out there. It's not clear, does anyone really know what's going on yet? So Venus can maybe help us understand this. So we've handled the first. Let's look at, is it geologically active or is it dead? This is an interesting approach that astronomers use, where they plot crater diameter in kilometers versus the cumulative crater frequency per square kilometer. And basically what that tells you, given the constant bombardment of planets or bodies in our solar system, the age of the surface. So this is actually from moon data here. So if you look at this, Mars is on the left. So Mars has about at least 100,000 craters on its surface. If you use the data that I just had on their slide, you come up with an age of about 3.5 billion years, which is about when we think things basically stable, the volcanic activity and geologic activity stopped on the planet. So this actually makes a lot of sense. Now, if you look at Venus on the right, you only have about 1,000 craters. It gives you an upper age of less than 1 billion years, probably as young as 150 million years. So it's a very young planet on surface-wise, just like the Earth is, very comparable. So is it dead or alive? This is actually from the Venus Express from ESA sent out. And they looked at surface chemistry as they flew by. And these red areas show different compositions than the other areas, showing that looks like you actually might be capturing lava flows coming down the side of these volcanoes. And if you look at the atmospheric chemistry, you're seeing sulfur dioxide and other ingredients which come out of volcanoes. And then also you have this on the bottom right here. You can see this is basically emissivity, which is basically how broken up the surface is of the planet. And so these light areas are very broken up, probably representing young lava flows versus the darker areas, which are older flows. This is from Hawaii. Anyone who's been to Hawaii knows that dark rock surface to the sea. Lava doesn't just come out, it's interacting with the environment, and given everything I was just talking about, it's a dynamic process. So when lava first comes out, this is minutes. Look how shiny it is. But very quickly, within hours, it starts losing it, as you can see out here in the top left. And then within days, it gets that dark color that we're used to seeing. So this is a dynamic process when it comes out. And it's basically happening, it appears, on Venus today. Question of no tectonic plate boundaries. So when people got the early data from the probes, they jumped on it and said, oh, this is actually a feature on the Earth, and this is a feature on Venus. They said, these look similar, could be subduction zones. Remember I said before, subduction was the first step to getting plate tectonics going. But other people said, no, it doesn't have to be that. It could be a mantle plume. And I'll show what a mantle plume is soon. So this is basically Artemis corona, which is basically a typical shape for a plume, basically forming these circular shapes that come up. This is basically similar to how Hawaii's forming. It is based on the same principle. So this is what a plume is. Basically, you have a magma chamber that keeps expanding and ultimately cracks the surface, forming these circular shapes, spreading that out. And then here again, it's another shot showing very characteristics of what could be a plume. Now, if you have these plumes, it doesn't mean there's not subduction zones. You can see right here is subduction zone from the plume itself. That surface has to go someplace. So you can argue Venus looks like it has potentially plumes, which means it probably has subduction zones, and yet it still doesn't have tectonics or a magnetosphere, a magnetic field, as we know it. This is just another look at that, looking at how these things, and this looks like recent volcanism on the surface. This is an interesting one. This is showing at Magellan resolution on Earth. So if we look on the left here first, we can see this is data from satellites near Earth orbit or low Earth orbit. And these, you can see the San Andreas fault, and other faults in the region. If you put that same data at the resolution we have from Magellan, look how poor it is. It's hard to tell anything. So we're actually working off of very poor data. So if you say, what do I want to do with the future probe? I want a lot better resolution of these surfaces. So let's look at those myths and how they're busted. First, Venus may well have been the first habitable planet, and it may have remained habitable for billions of years. So saying it's outside the habitable zone, true today, but not true in the past. Is it geologically dead? It's very likely geologically active today. And its average surface age could be as little as 150 million years. No plate boundaries. Venus appears to have subduction today, the first step in plate tectonics. But studying this could help us reveal, how does it even start? Again, we don't even understand how it started on our planet, let alone on other planets. Keep in mind exoplanets and how we're looking at them, all this would apply. Concurrent questions seeking answers. How can a planet change over time? You know, are they always the same? And clearly they're not. We know our planet has done a lot of changes. Well, how does the conditions for life arise, and for how long? Could life have existed in Venus in the past or currently? Why does Venus not have a magnetic field? We're discussing. One I haven't mentioned much, but I'll get into in a little bit, is lightning. Is there lightning on Venus? You expect there would be. It has lots of clouds. You would think that it would have lightning. Did Venus have continents? About 7% of the surface, remember, is mostly a flat planet, but 7% is covered by these plateaus called tesserae, which is Greek for tiled. Could they have been the early continents? These are just some of the questions. Looking for answers. One last thing on this is potential climate scenarios. 3 have been proposed. Optimistic, Venus spent most of its life in a really nice surface liquid water, plate tectonics, stable temperature climate. Not so optimistic, spent about first 100 million years with a primordial magma ocean, CO2, steam atmosphere. And the last was initially nice, and then greenhouse effect took over, and it just cooked. Unfortunately, all 3 of these scenarios, if you do the modeling behind it, would meet the deuterium to hydrogen ratios that we see. So we really don't understand it yet. We have to get more data to understand it. Mathematical modeling continues. You've got the sun heating hypothesis, more data, essentially, it's a network of that. So I mentioned about a few years ago, there was a big hubbub about life on Venus. This comes around a molecule called phosphine. Natural production on Earth either by abiotic or by biotic processes. Abiotic, it's either by volcanic release or by acid reactions with impurities in iron. It's not a huge source of it, but it does produce it. Biotic, it's anaerobic decay bacteria in landfills, marshlands, and animal intestinal tract. I'm not expecting money landfills on Venus, but you never know. Right? Maybe in the past. So, back in 2020, spectroscopic analysis of Venus's atmosphere appeared to show phosphine in high concentrations that they couldn't explain by abiotic processes. And my personal feeling as a scientist myself, they were irresponsible putting out, must be life, because then that got all the news and everyone jumped on that. And, you know, as I said, basically, if you wanted to do biotic, then you need organic matter. But unfortunately, subsequent analysis showed they were wrong. Basically, they had made errors in the algorithms that when they were corrected show either no phosphine or a few parts per billion, which could be explained by abiotic processes. All right, that's all the science at that point. Now I'm going to go into the probes, what has happened and what's going to happen. But before I do that, are there any questions in the audience or online? Yes, sir.
Reconcile the two scenarios where you said life could have existed about a billion years. The surface was fairly young at 150.
Well, what that's saying is that the surface is refreshing. It doesn't mean that it's only 150 billion years, 150 million years old. It's refreshing itself, just like on Earth here. You don't find many craters on Earth. Right now, if you count the big craters, only count like 100 to 200 craters on the surface of the planet. It's weather. That's what we're saying. Does that make sense?
Yep.
Any other questions? Yes, sir.
What about the pressure? When you're talking about the presence of
It's true. Now, if Venus in the past actually miraculously did have plate tectonics and was actually having a dynamic processes like we have on Earth to control the CO2, then they may not have had the pressure they have today. So the question is, did they have it in the past and it stopped? Or did they never have it? We don't know the answer. Don, how do I check online? Okay. I got it. Chat. Doesn't seem like there's any. Okay, close that. All right. So I had to do a lot of searching on the web to find all the cute symbols for each of the 5 agencies who either have or will be sending probes out there. Okay, now it's not letting responding to be done. Tap on this. There we go. 30 missions successfully reached Venus. These are missions specifically aimed at Venus. There's been a lot of flyby probes. Surface probes don't last long on this planet. The record is the Russian probe Venera 13 at 127 minutes. Now, NASA's going to be sending out a probe I'll discuss in a little bit, and they're only predicting that it's going to last for a little over an hour. So I don't know why they're going to let the Russians beat us, but it seems like it. Okay. All right, let's talk about our friends, or maybe not so much friends, the Russians. They were very active from the late 60s through mid 80s, and they had a few failed probes at the beginning. Venera 4 was an atmospheric probe, and they had another one in 69. First landing occurred in 1970, and then they had several other landings, orbiters and landers, flybys, and then they even had some balloon programs with the landings. So what are the key findings from the Russian program? Venera 4, they were the ones who showed it's mostly CO2 in the atmosphere and no evidence of magnetic fields. Atmospheric pressure is 75 to 100 atmospheres, and they actually have beautiful data that you can easily grab off the web showing how that pressure changes with altitude. And the wind speeds, showing wind speeds up to 186 miles an hour. Soil is basaltic, meaning it's basically volcanic in nature, similar to Earth. And Venera, that's from Venera 14. And a beautiful by Venera 13 picture here, you can see actually from the surface of Venus with that sulfuric acid haze, giving that nice glow. I have an opportunity to sell you properties here if you want it. There's nobody's sold any yet. Okay, if that's enticing, let's go for it. Okay. All right, ESA mission chronology. They had back in 98, 99, Cassini flyby en route to Saturn, and the Venus Express. Love that term. What they found was an oxygen air glow. There's still oxygen in the atmosphere, amazingly. not a high concentration, but they were actually able to capture that on their cameras. And they got a hint that there was something electromagnetic that was short in duration. Was it lightning is the question. And southern hemisphere in the UV, beautiful image. Japan has Akatsuki. It's tough for me to say that. It means dawn in Japanese. They made a first attempt in 2010, and they had a navigation error. So then they had to work like crazy to get it come back. It took 5 years to get that to come back, but they got it to come back. And it's been studying the Venus climate and atmosphere ever since. Still there. They'll get weather patterns, determining impressions of lightning, and search for signs of active volcanism. What have they found? Cool one, which is the stationary bow wave, which is called a gravity wave. The gravity wave happens when you have two different density fluids that are interacting with one another, and they form like this stable wave. And you can actually see it in the ocean sometimes. Here's the bow wave. It's humongous, 10,000 kilometers across, and it occurs about 65 kilometers up from the surface. And the theory is it's proposed by mountains. We have bow waves. We don't have bow waves. We have gravity waves on Earth. Nothing like this. Never seen it like this. They actually have the presence of an equatorial atmospheric jet. We have the jet streams, but they're always at higher latitudes. Why? Because you have to have conservation of angular momentum. And so basically that's what's causing those high-speed jets circling our planet. Their circles the equator. Not sure why. Unusual pattern of streaky clouds across the planet, suggesting some interesting flow patterns. Not clear what that means yet. And the question is lightning. They actually got another signal that maybe there's something happening here, but not really captured. Let's go into that in a minute. So here's a cartoon showing the gravity waves. You'd have a high density fluid from the bottom hitting a mountain, being shoved way up within cooler air and hotter, less dense material here, more dense material up here, and they'd be mixing. So that's what causes a bow wave. There's been a 40-year search for lightning on Venus. No one's quite sure. Again, why would you want to do it? Because again, on our planet, we've shown lightning could be a first early step to produce some of the necessary ingredients for life. So it's seen all over the solar system. Our planets, Jupiter, Saturn, Uranus, all of we've captured images of lightning. These clouds, you'd expect it, even though it's sulfuric acid. But the Pioneer missions detected pings on the magnetic and acoustic sensors. We weren't sure what they were. Some spacecraft have detected some spacecraft have detected electromagnetic pulses on their flybys, but others have not. Like Cassini, didn't see anything. Then in March of 2020, 5 years after they started on the planet, they saw a flash in the atmosphere. They captured it on both their lightning and airglow cameras. Problem is, it was a one-time shot. Was it lightning or was it a bullet? No one knows yet. So this is still an outstanding question about Venus. Now let's move on to, due to our heart, my heart, NASA. 62 was the first at Mariner, it was flyby, then they had Mariner 5 in 67. 73, Mariner 10 with the gravity assist en route to Mercury. Pioneer, Magellan, which we've been discussing in 89. Galileo, en route to Jupiter. Cassini-Huygens en route to Saturn, and then Messenger, Houston. What did they find? They've been extensively imaging the planet at various wavelengths. They've mapped about 70% of the surface down to a resolution of about 120 to 300 meters. Still not as good as what the geologists want to see. Like the data we're using for the Earth, the resolution is generally like several meters, because it's really important to know the altitude as well as the longitudinal changes to really understand the geology. Cloud droplets or sulfuric acid, no magnetic fields have been confirmed. Flat topology that we were showing you, that's where that came from. And interestingly, the atmosphere is relatively clear once you get below 19 miles. You just take that swim through those sulfuric acid droplets and you're good to go. Then you'll be crushed and cooked. Okay, sorry, maybe not. Surface temperature measurements extensively. All right, planned future missions. 3 different space organizations have said they want to send craft there. First is the Indian Space Organization, the Sukhrayan 1 next year. NASA's got 2 that they recently announced, Veritas and Da Vinci, towards the end of this decade, early next decade. And then European Space Agency has Envision. for early in the 2030s. So Brian, what? Launch next year, 4-year mission. Thank God I don't have to say this. What is it? It's an orbiter. Okay, it's not going to land. Primary research areas. These should come as no surprise after all this discussion. Surface, subsurface, stratigraphy, and resurfacing process. Stratigraphy is basically the layering of a planet on the surface of the planet. Atmospheric chemistry dynamics and interactions of the ionosphere with the solar wind. Since it doesn't have a magnetic field, what's actually happening here? All right. Veritas, Venus Emissivity Radio Science, INSAR, which is basically synthetic aperture radar, and topography and spectroscopy. This will launch December 27th, approximately, if you believe the timelines from NASA, and reach Venus about a half a year later, a little over. What is it? It's an orbiter. Primary questions: what processes shape the planet evolution? Geologic processes are currently active. Just confirming. Is there evidence of past and present water? Now, as we all know, life is full of ironies. This is a photo. You can't probably see her name here. This is Sue Streetcar. She's actually a planetary geologist who I stole a lot of her slides. So thank you, Sue. She's the lead scientist for Veritas. And she's taking a picture here in front of Venus, PA, so our own state. And why she take a picture there? Because her father was born and raised in Venus, PA. So life is full of irony. Where? It's, what's that? Yeah. I think it is. It's near Mars. It is too. It's west of here. So what is it going to do? We could go on for a whole talk on just what these probes are going to do. High resolution radar maps of the surface, near global map of rock type, iron mineralogy, surface weather. Given that we wanted to understand, are those tesserae continents, not continents? What is the surface? You can see why you're doing it. Find estimates of Venus core size and composition. Scientific equipment on board varies. They've got the radar. They're going to get really great resolution down to 5 meters. Emissivity mapper, again, roughness of the surface. Gravity science. It's interesting how they do the gravity science. It's actually looking at perturbations of the probe as it goes around the planet. And they actually have technological demonstrations. You know, they always want to take opportunities every chance they get. And this one is actually a deep space atomic clock. So they want to do a test of it, because if it works really well, they're going to use it on future autonomous missions and probes. So it could be a very interesting one. I need more water. Could you give me another water, somebody? Scientific objectives. I'll just let you read through some of these, or I'll just pick a few out. Thank you very much, Dave. You know, is water in the interior being released by the volcanoes, or the plateaus, tesserae, the continents, etc. So these are all the questions we've just been talking about. The next probe from NASA is Da Vinci. Deep atmosphere of Venus investigation of noble gases, chemistry, and imaging plus. What's the plus, you might ask? They're actually going to have a lander on this, so there's actually imaging on both the orbiter and the lander. So that's the plus. Launch basically 2029, 2030. It's an orbiter and an atmospheric probe. It's going to be the first spacecraft to enter the atmosphere in 40 years. 2 flybys of Venus are going to happen first before it releases the lander. Scientific questions: atmospheric origin and evolution, composition, and the surface properties. What we'll do, it's going to do emergent sensing of the surface and the atmospheric circulation. The probe is actually going to land on Alpha Regio, one of those continent potentially places that we've been talking about. And it's estimated to last about an hour. Again, I'm going to see if we beat that. Scientific instruments on board, they have several spectrometers, as well as atmospheric structure investigation, temperature, pressure, etc. The orbiter actually is going to have a suite of cameras from UV to near IR. So we're going to be doing simultaneous work. And then again, not to lose the opportunity, 2 technological demonstrations on board. One is studying clouds using compact UV and visible spectrometer. The other one's a actual student collaboration. I don't have any real data on it, looking at Venus oxygen fugacity experiment. Fugacity is basically a thermodynamic term for correcting ideal gas laws to reality. So that must be what they're doing, because the pressures are really high and temperatures, it's not going to be an ideal gas whatsoever. I used to live that world, so I know that really well. So this is again a picture of that Alpha Regio region of Venus in probable land. It's going to be fascinating to see what they get and the pictures they get from it. Again, sits up 1 to 2 kilometers from the surface. It appears to be older. It actually might have a lower density. Again, that would go with the composition, might actually be a comet. Here's some of the scientific objectives. And basically, it's very similar. So I'm not going to read all that to you. And our friends at Europe, they can't be outdone. So they announced Envision. It's going to launch basically in the early 2030s. Low altitude polar orbiter. So it'll be a different orbit, trying to get the whole surface mapped. Basically looking at current geologic activity, surface features. Is it ever life? Is there an ocean? And then the geodynamics, really trying to understand the heat balance of the planet is going to be an interesting one in this one. You know, why don't they have tectonics and a dynamo to produce a magnetic field? And this is a cartoon I like. I stole it. So if an alien from Mars is called Martian, there's an alien from Venus, a Venetian. You can see the little blind here. I did go on a tour of Venus, of Venice once, not Venus, Venice once, and the tour guide was a real Venetian. So I actually have met one that didn't look like that. So this is the end of my talk. This is actually a cartoon or a nice artist depiction of what one of those tesserae might look like with the volcanoes going off. And you can see the flat plains going off into the distance. So with that, any questions? I hope you've enjoyed the talk.
So could you talk a little bit more about the rotational speed of Venus? Because I'm understanding part of the dynamics of the Earth's magnetic field is actually because it is spinning at a different speed than the core. And that's one of the things that's generating that dynamo effect.
That's not what most scientists believe. Okay. I'm not saying all scientists, but the prevalent theory today is that core, that effect is actually occurring due to the cooling of the core, due to the crust using up the energy from the core. So basically the plate tectonics are driving that more than it is the rotation of the planet. It's not a frictional factor, because given that we've been around billions of years, think about it, it would have reached equilibrium long ago, you know, as far as between the core and the exterior part. Just like our atmosphere, we're moving at thousands of miles an hour, we have 1,000 miles an hour, but we don't feel the atmosphere move around us because it's actually in equilibrium with us, right? Other questions? Dave?
One of the interesting things that happen on Earth, any Earth that acts like pathway, it out pumped oxygen in the system and gave it great way to soak up carbon. That's one of the things that I missed to help it.
It's very true. You know, I mean, it's a huge thing, and life has modified our planet. Not only are we doing it, but the life I was showing from billions of years ago clearly has modified the planet. And putting that oxygen there, it's a very reactive molecule. So it would have changed the planet dramatically. So I agree with you. Was it Bruce?
Yeah, you had mentioned a really pronounced axial tilt. And again, there's not one or several good theories as to why that may be, and does that, do you make any inferences that kind of extreme tilt being responsible for some of the extreme atmospheric conditions, etc., just because it's so different than those?
Yeah, it is very different. Now, again, if you think from the point of view of when did that happen,
right?
You know, I'm sure when it happened, if it say it did, let's say it did flip, you would have huge turbulences on the atmosphere. But that may have happened a billion years ago. We don't know. So it's not clear about the weather patterns and what that would have affected it. I delved into it quite a bit, preparing for this talk, trying to look at some of those theories. But there's so many of them, and it's all very complicated mathematical modeling, looking at the instabilities the planet would have gone through. With that heavy atmosphere is a huge drag on the planet. So you can model it that it's just a frictional drag on the planet, and that basically caused instability. and then cause it to flip. So people have been able to convince others that that's a viable approach. Did I follow all the math they went through? No, I didn't. But then the other, of course, is it just was such a drag, it slowed it down. And then given the interactions with the sun and the atmosphere, it slowly rotated the planet in the other direction. So those are the two primary theories today that I know of. Question online? Oh, we've never seen a break in the clouds with any of our probes. We've gone around it. The Japanese probe has been there since 2015, hasn't seen any breaks in the clouds. Now, interestingly, the solar probe, our solar probe, the Parker probe, went by, and it had a lot of infrared techniques on it that was going to be used on the sun. And when they were on the dark side of Venus, they actually used it on Venus, and they were able to actually see through the clouds to see some of the surface features in the infrared. And they were mapping it to the radar images, and they overlaid beautifully. So you could actually see those tesserae, and since they're higher, they're a little cooler, so they could actually see those differences. That's the only thing I know of where we've seen it. But as far as we can see, every picture we've ever seen of Venus, there's never been a break in the clouds. Other questions? You're welcome. Yes.
So the Da Vinci lander, seeing landers now that watching TV, possibly lands, and then there's this very methodical, meticulous, let's check out all the systems. We're going to wait to transmit data. You're going to get an out. How are they going to change the algorithm? How will we do that to get it?
Practically they're going to have to do it before they even launch it. They're going to have to make sure they have all the systems ready to go, because it's not going to have time when it hits the surface. You're absolutely right. Look how long it's taken the rover to get anywhere on Mars, and what they do every time they do one of these things. Like the James Webb, right now they've been doing meticulous detail things. It's taken months for them to get to the point where they're almost ready to take the first images, right? They get the very first image they ever did, but the real images. So I agree with you. But thermodynamics, you can't beat thermodynamics. You can do some tricks and try to slow down that heat penetration, but you got to chug the heat someplace. And there's no place when you're surrounded by the heat. So it's going to cook it. Every way we know of right now, other than you can do some materials that will actually react and then absorb some of that heat. So they can do some of that in layers, which you don't have to throw the heat anywhere because it's going into the reaction. You can only have so much of that. So you're right. They're going to have to do it quick. And I don't have the exact answer for you, but they're going to have to do it quick. They don't have time. All right. More than you wanted to know about Venus? I appreciate your time. Thank you.
Very much.
Well done. There were no glitches in your talk. The glitches were all because of the audio visual and the internet portion of it, but you gave a fantastic talk. Thank you very much. It is great to have so many NASA Solar System ambassadors at our disposal, and we certainly look forward to hearing more from you in the future.
Love to do it.
Don has also brought up that James Webb very soon will actually be getting us not just some collimation data on stars and that sort of thing, but sometime, I think it might be in June or possibly May if they accelerate the schedule.
Mid-May, we'll know the timing, but they're thinking it'll probably be available in July.
In June or July, that Webb may be getting its first real images. And that might be, normally we don't have meetings for like this in the summertime because we're busy outside with our telescopes. But it might be an interesting time for us to kind of hold a sort of an inter-summer meeting with the club to sort of share in this, monumental achievement that mankind has made here. And please stay tuned to both your emails and also to the club newsletter and our social media, because we will be announcing if we're going to be doing an event like that. Donna suggested it, and I think it's a great idea. It's something we can all share in. We can all certainly be interested in what NASA's going to show us first images from that. So anyway, thank you again for kind of seeing Bruce. Who's next up for next month?
So next month, we have Michael Brown with Caltech. He studies a lot of trans-Neptunian objects and hyperbell objects. And he has been one of the major advocates and done the most work on the elusive planet Nine. And that's what he's really talking about. Search for planet Nine, a lot of the modeling has been done. Michael Brown's also one of the guys that killed Pluto as a planet. So I told him, you know, it may not be well received, but anyway, he'll be giving a virtual presentation. And that'll end our until summer's over.
Unless we have a sort of informal get together for the winter. So anyway, I'm sure that many of us have felt over this winter that the surface of Pennsylvania here was very much like the surface of Venus, always covered by clouds. But that is starting to change now. In fact, it's clear out there right now. The seeing ain't great, but at least it's clear out there. Grab your telescopes. The weather's getting warmer. Looking forward to seeing you all at BVA and subsequent events. Peace, everybody.
What's the next event?
Huh?
Next Friday. Next Friday.
Next Friday.
Where's that gonna be?
Next Friday with Girl Scouts.
Friday with the Girl Scouts. Did we get cookies?
Look at the data. That's fine.
Yeah.